Welcome, everyone. Very good afternoon to you. So this is the second for the Electrical and Biomedical Engineering webinar series. This is being conducted through the IEEE's EMBS Phoenix chapter. EMBS is the Engineering in Medicine and Biology Society. We, as a society here, our primary objective is to equip industry professionals with knowledge of breakthrough technologies, prepare them for careers in healthcare and engineering fields, and also to promote collaboration between industry, academia, and government. This specific webinar series that we've designed, it offers professionals, industry, academia, and research institutes a comprehensive view into the top electronic and biomedical trends and technologies of today and in the future. The talk for today is Introduction to Medical Imaging, and this has been brought forth by Dr. Jeffrey Vaitekunas. Dr. Vaitekunas is currently the assistant teaching professor at the Pennsylvania State University. And I'm going to give a little bit of an introduction to Dr. Vaitekunas, who I actually had the privilege of working with in one of my past careers. So Dr. Vaitekunas has a long list of accomplishments. So he actually has a doctorate in biomedical engineering from the University of Cincinnati. He received his master's in theoretical and applied mechanics from Northwestern, and his bachelor's is in EE from Purdue. He currently holds over 25 US patents for ideas ranging anywhere from ultrasonic surgical devices to advanced image processing techniques. He also has 25 years of experience in medical device fields and has worked at a slew of industry at companies at Ethicon Endosurgery, Omnisonics, and other companies. Dr. Vaitekunas is also formerly the president of the Ultrasonic Industry Association and has served as the board of directors for the association. And to top it off too, he's also licensed to practice law in the US Patent and Trademark Office. So we are very excited and pleased to have him on board for this presentation. And we hope that it brings a lot more insight to the industry and professionals and the listeners here in the area of the medical imaging. Before I begin, just a couple of items for the listeners here. So I would request everybody to please turn off your videos if you have it on, just to preserve the bandwidth, as you see a lot of people joining in. We're also requesting everybody, if you're not already, to please be on mute. Brian Pelzik, who is the treasurer at the chapter, the EMBS chapter, will be moderating the Q&A session, which we will have later in the presentation. We'll give around 10-15 minutes to answer any questions that the listeners may have, and Brian will be moderating that. Myself, I'm Asim Singh. I'm the program committee chair for the EMBS Society. So without much further ado, let me introduce bring forward the speaker who's gonna give the presentation here. Jeff, take it away.
Okay, hello everybody. Can you hear me? And can you see my monitor mouse?
Yes, Jeff. It's good. Go ahead.
Okay. So thanks for coming, and let me give you a little background. I actually have been teaching at Penn State Behrend for the last 4 years after my industrial career, and I am teaching a course, an introduction to medical imaging. So what I ended up doing was taking some of the best of the slides from that 3 credit hour course and condensing it down into I think hopefully an interesting discussion where we're going to talk about imaging in general and medical applications, but then end up with computed tomography. So if you're not, if you don't know how computed tomography works, we're going to give a little primer on that, and I think I hope you'll find it interesting. All right, and already a snafu. There we go. Okay, so no biomedical presentation is complete without starting with some biology. And since we're talking about imaging, we're talking about something you see. And so I wanted to spend just a couple of quick slides to talk about when you look at an image, you have to understand that, you know, what it is you're looking at. You have to understand the receiver from what you're looking at. And in this case, we're going to look at the eye as the receiver. And here is a cross-section of an eye. You have a lens. And the point I want to make it here is what's called a fovea. There's the little point down here called the fovea, and that would be your center of vision, what you would call right in the middle of your view. And then just to the left here, so this would be the right eye, just to the left here is your blind spot, and this is where the optic nerve comes out from the eye. And there's literally no vision in that area, so you are blind in that point. And we're going to look a little further about the fovea means. So the fovea is your center of imaging, which is here at 0 degrees. And then we're looking out, plus or minus 80 degrees horizontally from the fovea. And the point I want to make is there's different, you discern color and you discern black and white if you have normal vision. And so there are rods and cones, and I know this is probably a little lower level than you're used to, or I apologize if you know all this, but I want to make a couple of points. So the rods, if you look here at the dashed line, that is the density of the rods, and if you look at the solid line, that's the density of the cones in the eye, in the retina. And so you'll notice a couple of things. One, there's no vision here at the blind spot. There's no rods or cones, so you can't see anything. And then in the center of the vision, what you'll see is there's a lot of cones and no rods, or effectively no rods. And just outside the vision, there's a lot of rods and very few cones. And so what that means is your color vision is all right in the center of your view, and your black and white vision, your low intensity light level vision is off to the side. And if you're not familiar with it, this is why if you look at a star in the sky and you look directly at it, sometimes you can't see it. But if you look just to the side a little bit, you can, and that's because you're switching from the cones, which can't see the dim light, over to the rods, which can. And so that's why that happens. And so recognize that our vision, only in the middle do you see color. But when you look at an image and you look at the world, everything's in color through your entire peripheral vision. And the point I want to make here is that that's your mind filling in information. So there are some cones there, and so there is some perception of color. But your mind plays some tricks on you, and I want to just point that out to people if they're not familiar with it. So looking now just at the colored, the color absorbing versions of the retina, there are 3 basic anatomical structures that you can use in the eye, that the eye uses to see light. And it's interesting that the red and green overlap, and the blue is a little separated. So your red and green are kind of similar and have an overlap, and your blue, and you only really see red, green, and blue, and then the combination of the intensities, just like an RGB video screen, the intensity variations allows you to see all the colors. What I find more fascinating, and the reason I wanted to show this slide, is because if you look at, again, looking here at the cones, right, the colored portions, 64% of your cones are red, approximately, right? 32% are green, and only 2% are blue. So 2% of your optical reception is in the blue wavelengths, and everything else is in red and green. And I don't want to go into great detail here, but if you look at chromaticity diagrams, you'll notice that blue is one of the harder colors to perceive, and there's a lot of red and green that inundates us, and that's because of anatomical situations. It's a very real thing. I also don't want to go. I'm a real fan of optical illusions and the eyeball, what the eyeball sees, what you perceive versus that, and what does color mean. And we don't have time to go into all that detail. But if you're not familiar with this, I just wanted to point out a couple of optical illusions that you should be aware of. One is the Mach band effect. So if you look at these gray scales, most people perceive that just to the left and just to the right of where there's a difference in grayscale, you have a perceived intensity. So you have a little lowering of intensity on the left side and an increase of intensity on the right side. In reality, these pixels are all absolutely flat. There's no band. And so if you're seeing this Mach band effect, that is your perception, and that is not the reality. And so I just want to make a point to people that when you're doing medical imaging, when you're creating images, when you're looking at images, not only do you have to deal with your receiver and your display, but you have to deal with how the mind is perceiving what's being displayed. So you have to be very careful. Another one I'm not going to do. This is only the second one, I promise. But all these grays in the middle are at the exact same intensity, but they are not perceived that way. So again, I'm not going to go further there. However, let's look at displays for a second. If you're looking at an image, any image, medical image, you have to understand your display. And I'm not sure that people recognize or realize this, but RGB, which is the red, green, blue format for a pixel. So if you have a pixel on a display, you typically have a red, a green, and a blue, light emitting something, right? A LED or something. Beware of your display. If you're working in the medical device field and you're working on optical imaging systems, you have to know your display because, for example, this is just an example, the Galaxy S3 phone actually has RGBG, red, green, blue, green for every pixel. So every pixel has two greens, one red and one blue. So if you're doing image processing or you're doing anything like that, you have to be aware of that from your data sets and your data files and how things are presented. All right, that's enough of biomedical background and your perception of images. Now I want to get into the focus of the talk, which is absolute medical imaging. And what's the purpose? The purpose of medical imaging is to diagnose disease, right? So you can make plenty of pretty pictures, but if you don't diagnose something, it's not doing its job. And so, for example, this is just an example here, but this is a MR image, magnetic resonance image. And there are two this is the brain, this is the head, this portion of the brain, and there are two white matter lesions in the brain here in this particular patient. And if you look here at the top in image A, you can see one there, where the point arrow to. So look at B, C, and D. These are three different versions of that same image. And we look at, what do you talk about when you talk about perceiving an image? And when you can diagnose a disease, we can talk about three things that are most common: resolution, signal to noise ratio, and contrast to noise ratio. And so this same image with 4x poorer spatial resolution, still a pretty good image. In fact, I can still see those two white dots. So, yes, the better the resolution, the better discrimination you're going to have. But again, if you have 4 times less resolution, you can still do the diagnosis here. Signal to noise ratio. If you've got more noise, you have a lower signal to noise ratio. This is what the image looks like. It's 4 times reduction in signal to noise ratio. Again, you can still make out the dots. So signal to noise ratio, all these three are important. You have to understand how they contribute to what you're looking at and to your ability to make a diagnosis. And then the last one here is a contrast to noise ratio. And in this one, I would argue that even though I know they're there, right? So I know those two dots are there, so I can make them out. But if you didn't know they were there, I would say with your contrast to noise ratio, you would probably not be able to make that diagnosis, or it would be easy to miss. And so whatever your type of imaging, you have to beware of, right, what you see, what you perceive, and also what the display is providing, and then how those work together. So we don't have time to go through all the medical imaging modalities that are available, but I just want to point something out here, and I have a few examples. So here's the electromagnetic spectrum, everywhere from gamma rays to radio waves, right, the entire gamut. And what I found fascinating as I put my notes together for this course is that we image throughout the entire spectrum. The human race has been able to really take advantage of what's available to us from a physics standpoint, and it's really fascinating. So I'm not going to spend a lot of time on each, but I just want to give you all an example of, these are very real images from very real diagnoses of a disease. So we're going to start at the left side. We're going to start at gamma rays, and we're going to work our way through to radio waves. So gamma ray imaging. Just the top two I'm only going to refer to right now. The first one, A, is a bone scan, and the second one is a positron emission tomographic image. So these are, gamma radiation, and you can, through the same mechanisms we're going to talk about for CT scanning, you can capture the information that's being emitted from the patient, and then you can convert that into an image, and you can use that image to diagnose a disease. And in this case, when you're looking at a bone scan, you're looking at the absorption of radioactive isotopes in the bones. If you're looking at somebody that has bone cancer or diagnosing bone cancer, you can make a diagnosis. So from gamma rays, we're going to go to X-rays. Everybody's familiar with X-rays. I'm not going to spend any real time on it, but here's an X-ray of a patient with some cardiac leads on their body. If you've never, I don't know how many people have looked at X-rays here, but that little dot there in these lines in the X-ray, those are cardiac leads. You've got the bones, the usual things. We're going to talk about CT later in the little lecture here, but I just wanted to go through all the different capabilities. CT, by the way, down here on the left. This is a computed tomographic reconstruction, again, of a head of a patient. So this is planar X-ray, where you have a single plane. You're taking X-rays. They're being transmitted through the body. They're absorbed at different levels, and then you're displaying the information. And we'll get to tomographic reconstruction at the end of the presentation. So moving on, ultraviolet. So ultraviolet, you can make images from ultraviolet. These are corn, so this is not biomedical, but it is physical. So you can look at corn smut by looking at ultraviolet imaging. Light microscopy, everybody's familiar with light, but I'm just working my way through the whole spectrum. So obviously light. Infrared, right? You can look at thermal output, and this is a thermal infrared imaging from satellites of the northern and southern hemisphere. Just looking at what the heat output is. Obviously, for people that are familiar right now with COVID-19 temperature screening, if you've gone into a hospital lately, you've had to stand in front of an iPad with a thermal sensor on it, and you've had to have your temperature taken using the infrared. This is relatively new, millimeter waves. So for a long time, millimeter waves weren't really used for anything. They didn't have a lot of practicality. And then along comes the TSA and the airport screening and looking for contraband. And so you step into one of these TSA screening devices, and the millimeter wave system takes an image, and this is what an image looks like. So this is a millimeter wave image. You don't typically get to see them because they do show some information that some people find to be personal. But it does a great job. It can see through clothing and see what's underneath clothing without going so deep into the body that you're looking at interior structures of the body. So that's the whole point of the millimeter wave. And again, that's why I didn't really make a lot of, it was more recent that it came out, because it's not really good for looking inside the body, and for diagnostic imaging, we typically want to look inside the body. So moving through the spectrum, now we're looking at radio waves, and so we're looking at a magnetic resonance image. So this is where you take a huge magnetic field and you apply it with a gradient, a primary gradient, and then a second electric field, a magnetic field, and you bang it, and it causes vibration of the materials in the body, and then the radio receiver picks up the radio signals, and then you can reconstruct those radio signals into an image, and you get some really, really nice, detailed, fascinating images. And the advantage of MRI over other imaging modalities is that it allows you to see soft tissue. So in this particular case, you can see that there's a bone. By the way, this is a knee. If you're not familiar with it, this on the left side, this is a knee. This is the top of the femur and femoral. And then this is the knee structure. Here's a kneecap, and then there's cartilage between the two bones here, and you can actually see the layer of cartilage. So if you have knee damage to your cartilage, you will have had an MRI, because CAT scans and other techniques can't really image it properly. And so what we're seeing is that all these different wavelengths that are available to us from physics show different things, and we can discriminate diseases by the appropriate application of those modalities. So that's through radio waves. And then we have the one that doesn't fit. So the one that doesn't fit is ultrasonics. So ultrasonic imaging, been around a long time. If you're not familiar with it, this is a fetal head in utero, and a baby, the body of the baby in the mother's womb. And so there's some vessels down here, but This is the only imaging modality that doesn't use the electromagnetic spectrum. So it's very interesting to me. I actually have quite a background in ultrasonic technology. And so I'm fascinated by ultrasound imaging, but and ultrasound propagation in general. But this does not use electromagnetics, so it's a completely different modality. The modality is pressure waves. It uses pressure waves and acoustic intensity, acoustic variation between different tissue types. And so the reason I bring it up for medical imaging is that this is one where you can get completely different information than you can using the electromagnetic spectrum. So the combination of ultrasound and other modalities combined can provide, modern medicine is just truly, truly amazing what we're doing. So given that, the most interesting thing that I find, and if you're not familiar with it, I want to give you enough information so that you understand how it works. It's this tomographic reconstruction. So tomographic reconstruction is within my lifetime. This is within something that happened while I was alive, and actually while I was already a professional. 79, Hounsfield and McCormick won the Nobel Prize for the application of tomographic reconstruction, for the ability to do it. And it wasn't until the 80s, low to mid 80s, that CT systems became possible, I guess I would say, or commercially viable. And today there's one in every hospital. There's more than one in every hospital. So pretty much, it's an amazing technology. So just what I'm going to do is give a little talk about how does that work? How do you do that? How did they get that Nobel Prize? Well, and if you understand it, it looks like it should have been obvious, but it clearly wasn't obvious if you get the Nobel Prize for it. So what we're going to do is talk about the spatial domain, and we're going to talk about, and I'll talk about later, the frequency domain. But this is a spatial domain, and you have a function x and y. And function xy is just an image, right? It's a pixel on an image. So let's simplify things and get rid of color, and let's just talk about intensity and look at black and white grayscale. And we're going to say that there is an image and there's a pixel at the XY location that has a certain intensity. And if you look at a line of the image, there'll be a function, which is the individual pixel information. It's often easier to look at transform theory not from the discrete perspective, but from the continuous perspective. And so what I'll say is that this function for our image is digital. It's discrete. It doesn't mean you can't use a continuous function. And we're going to talk about continuous functions for a little bit here, just to kind of organize ourselves into what I'm talking about. So you've got your function, which is let's say a continuous linear function. It doesn't have 2 points in the y for any x, and it doesn't have discontinuities. You're going to go through some form of a transform, and you're going to end up with another function that we're going to call this t, and it's going to have different variables, u and v. So we're going to transform from the spatial domain to a different domain. And the one we're going to be talking about is the frequency domain. It'll be the Fourier transform in the frequency domain. Then you perform an operation on the frequency domain data, and then you have an inverse transformation function. So you take the operated upon function, the function, in this case the frequency function, you perform the inverse transform, and you get out of it another spatial domain function, and that function now has been operated on in the frequency domain. So what you're doing is you're converting from in an imaging standpoint, you're converting from the spatial domain to the frequency domain. You're doing an operation in the frequency domain, and then you're converting back to the spatial domain. This concept is where CT is allowed. So this is nothing new here, right? This has been done since Fourier's time, which we're going to talk about. So it took from the 1800s to 1979 for somebody to figure out how to use this and turn it into a CAT scan image. So just a quick refresher. I'm not sure who the audience. I know who the audience is. I'm a member of the IEEE, but I'm not sure where everybody's at from a perspective of remembering their Fourier transforms and frequency domain operations. So I'm just going to run through real quick. So Fourier's whole idea in 1807 was that you can represent a continuous function by a weighted sum of sines and cosines. And sines and cosines are just sinusoidal signals, right? So there's different frequencies here. So basically, you look at different frequencies, you weight and sum different frequencies, and you can create a generic or general linear function as that combination of. So it's a Fourier series is what we're talking about. You're just taking a Fourier series. So the idea was, okay, so if you got a Fourier, if this works, right? So you have three. In this case, we're just showing three, for example. Three frequencies: frequency 1, frequency 2, and frequency 3. You combine these two together, and they have different amplitudes and different frequencies. You combine them together, you get this function that we're talking about, the function we're going to transform. You perform a Fourier transform on it, and you get the frequency domain information of the time domain function. So you have a function that in the time domain, you do the transform. Time is now taken out of the equation, and you're left in the frequency domain, and you end up with this. Now, these are sinc. You're not familiar with it. A sinusoid Fourier transforms into a sinc function. So these are sinc functions. What do you see? What do you notice about these three sinc functions? They have frequency f1, f2, and f3, right? That's where the peak is for each sinc function. So f1, f2, and f3. And they have different amplitudes, and the amplitude of the sinc function corresponds to the amplitude of the time-based function. So every piece of information, this is the point I want to get to, every piece of information that's in the time function is in the frequency function. But there's a cool thing about the frequency-based function that allows CT to happen. So we're going to talk now. We're going to move into the discrete world. So this is done using image processing. And so X-rays used to be all on film, and then people learned how to detect X-rays discretely. And there's a bunch of sensors now. So you take a sensor, you can sense the X-ray absorption along the path, and you can take a line of information that's discrete, and you can turn it use a discrete Fourier transform to transform it from the spatial domain to the frequency domain. And that's what's shown here. And for those of you that recall. When you do that, you get an infinite repetition of the function because the DFT creates the spectrum, right, the power spectral density, if you will, and then it repeats itself every period. So you have so you only need one full period to gather or retain all of the data from the initial discrete function, and the data is now frequency based. What I mean by that is you've got let's say DC or zero frequency. What does zero frequency mean? I think of it as DC current, right? I think of it as the intensity, the base intensity of an image. It's whatever the overall intensity is. There's no variation and spatial variation, and it's all just intensity information. And then at different frequencies, you have different levels of amplitude, given frequencies above and below the zero frequency, until you get to the maximum frequency that you were able to resolve with your Fourier transform based on the number of samples you have. It's interesting that the spectrum, you can position it anywhere you want. You define where zero is, right? You can say, okay, I'm defining, this is where I'm going to put zero. And what I mean by that is you can actually rearrange the location for where zero frequency is on your image. So I'm going to go to my next slide, and the example is here. So here's a very simple image. It's just a black background with a white rectangle in it. And you perform a discrete Fourier transform on that, and you get the image on the right. And the image on the right doesn't look like much. And it's hard to see, but if you look in the very corners, you'll see that there are white dots. There's white information here. There is information in this image, but it's hard to discern. And so what you can do is you can center the spectrum. So again, when you just look at an image, X, Y, and you put 0, 0 up in the upper left-hand corner, you end up with zero frequency in the upper left-hand corner, and it's hard to visualize what that means. But because this is frequency domain information, you can say, all right, I'm going to make zero. I want to make the center of the image be zero frequency, right? and then rearrange it. And what they've done here is they've done a log transform so that you can actually see more of the variation in the data. And they've centered the frequency, and you end up with this image down here on the right. So this is the spectral, this is the Fourier transform spectral image of this rectangular object with the frequency centered and the intensities log transform that so that they're easier to see. This is without the log transformation. So the information is still there, but it's harder for us, and again, perception, right? It's hard for us to perceive because the intensities are so low on the outside edges that we can't discern them. So we do the log transform. Again, all this information is retained. There's the information here is the same as it is here. It's the same as it is here, right? All three of these have the same information. The log transformation, all it does is map intensities so that they're easier for us to see. And just a couple of pieces of, just for people that aren't familiar with looking at Fourier spectra of images, if you take the image, you take the rectangular slit here and you move it to the side a little bit, you get effectively the same Fourier transform because most of the spectral information is the same. If you rotate it 45 degrees, you rotate the spectra 45 degrees. And so we got to, if I've done this a bit, doing the Fourier transforms and optical image processing. And after a while, you can start to make sense of some of these. Not that I could look at this and say, I know it's a slit. I don't. But you start to see some similarities in what's going on. So here's just for people to who haven't done this, for you to get an idea. This is a picture of a building, and it's got some nice edges and angles to it, which is why I selected it to present. And this is the Fourier, two-dimensional Fourier centered spectra of that building. And what you see here is right in the middle is zero frequency, right? And then everywhere outside of zero frequency is different frequencies of the image. So there's a big, you can even see it, a big sinusoid here, right to the peak of the roof. And then there's the windows are periodic. And then there's you get the idea. There's a lot of periodicity to this image, and you see it in the Fourier spectrum. You can see, all these angles and repetitions that make up the data. So the data is there. So taking that information, taking information that you can do a Fourier transform, you can transform a discrete piece of data to its spectral data. We're going to take the planar X-rays. You take an X-ray source, you shine it onto a patient, and you put a detector beneath the patient, and then the detector detects the number of X-rays that hit the detector, and some of those X-rays are absorbed by the patient or reflected or whatever, and you end up getting a planar X-ray image. And so what you see is that high density things are lighter because more energy was absorbed by the body, and lower density, like the lungs here. So this is the collarbone, the spine, right arm, left arm. And then here's the right lung and the left lung. Patient's facing up, that's why this is right. And you see that the lung has not a lot of attenuation. So, well, how's that done? Just real quick, for people that don't, I find it fascinating. So you take a tungsten wire, you wind it up, put a lot of current through it, you turn it red hot, it starts emitting electrons. You put those electrons in an electric field. They accelerate, and they hit a target. In this instance, I think the target's tungsten, but I'm not positive. The target rotates. Why does it rotate? Because if you didn't rotate it, it would get so hot it would melt through where it's being hit by these electrons that have been emitted. And when the electrons hit the target, they emit X-rays. Those X-rays then exit out the X-ray tube, and that's what goes down to the patient and that's what goes down to the patient and is absorbed by the patient. Talk about newer technology. This is very interesting. You can actually change the intensity of the X-ray, change the electron volts, change the wavelength, if you will, by using two sources. So you can have two separate sources, the same anode, creating two spectrum of X-rays. So you can have X-rays at two different spectral points, and you can discern more information. So this is in use right now in modern CT systems. They're actually using multiple energy sources to get more information to be able to discriminate more of what's going on in the body. Here's just real quick. Here's a picture of a fluoroscopy system for interventional radiology. If you haven't seen these things, they're great. Every hospital has at least one of these. I've been in hospitals that have a suite of 3 or 4 of these rooms. There's your patient lying on the bed. You've got the transmitter, the X-ray source. You've got on the bottom, you've got a detector, or in this case, the X-ray source may be down here, and detector on top. But you've got a detector on one side of the body, source on the other side of the body. And X-ray is going through, and in real time, the doctor can actually watch what's going on. They can watch the heartbeat. This particular doctor would be somebody that would place a stent into a heart for somebody that maybe had a heart attack. High cost equipment for the hospital, millions of dollars. So amazing what we can do as a people when we set our minds to it. We're going to go back to X-rays, and by the way, here's a CT scan system. We'll get that in a second, but that's what I want to get to the CT. But before that, I again want to talk about this function that we're looking at. Here's my continuous function. This is just a target. There's X-rays. This is assuming there's X-rays coming through. You've got a detector. The detector is at an angle phi from, just arguably an angle phi from an arbitrary position. And if you have objects, a first object here is the light gray, and then a medium gray, and then a dark gray. And these are different absorption levels of X-ray. You'll end up with a function that looks like this. So you'll end up with, because the path length here is short, the absorption is short. Because the path length here is longer, the absorption is more. Because the path length here has a higher density, it has even more absorption. And because it's an even higher density, even though it's a smaller path length, you still have more absorption relative to the first plane. So this would be planar X-ray. This is what happens in an X-ray machine. Computed tomography, you take that idea and you take the detector and you rotate the detector around the body. So you've got an X-ray source and typically a line detector or an array detector, and you rotate it around the body. You send the X-rays through, and the X-rays go through at multiple angles. You capture that data at those multiple angles, and then you reconstruct using this tomographic reconstruction. So here's a head, right? Here's a patient's head. We're going to say it's in the computed tomography system, and we're going to be rotating the X-ray machine and the sensor around the head. And what we're going to do is we're going to have X-rays going through the patient's head. So let's say they're emanating from the lower right here. They're traveling through the head, and they hit the detector on the top. And then the detector provides a function right here, G, right, which is the intensity received of X-rays at any path at that angle. And that's where this computed tomography really comes into play. So remember, this rotates around the head. So you've got an angle here, an angle theta, right? And you're sensing the density, the summed density through the head at every point along the line at that angle. And then as you rotate it, you get the sum at every other angle. So at this particular angle, you have the sum intensity. You go to the next angle, you get another intensity. That information is the spatial information. So if you take that spatial information at each angle theta, right? So the only thing that's changing as you rotate around the patient's head is the angle theta, and you're getting density information along a function at that angle theta. If you do a Fourier transform of that projection, it gives you the it gives you the frequency information from the spatial information. So you take the spatial information, you convert it to frequency, and remember what I said before. The frequency information is available to you, and you can as an engineer, let's say, you can define where zero is. So again, we're shifting our image now. We're shifting zero. We're going to say, okay, I'm going to the right side here. So this is the spatial domain, And on the right here, we're going to look at the frequency domain. So you take this spatial information, you do the Fourier transform, and that Fourier transform gives you the frequency information at an angle theta of rotation. So you center that spectrum at 0 here. You define 0 frequency to be in the middle. You define the angle theta as the angle that you were at when you made your sensing, and you can actually fill this line in, this dark line, right? This dark line is now the frequency spectrum of the X-ray information through the head at that angle. And the magic of tomography is, because you're in the frequency domain, regardless of the angle, you can set 0 frequency to be the middle, and then the angle of the sensor is just the angle theta relative to this first angle. So basically what you're doing is you're taking this image and you're filling the frequency data in here, and then you rotate a few degrees. You're going to have another line rotated a few degrees. You fill the frequency information in there, and you make a 2D Fourier spectrum of that person's head from that data, and then you do the inverse Fourier transform after you've filled in the entire spectral array at every angle theta. You take the inverse Fourier transform, and what that gives you is the image, right? It's the discrete, it's the slice image of the patient with all the information in, so that you can see the inside of the patient, only knowing the density absorption through the entire head at an angle. But by using this tomographic reconstruction, which is basically just an inverse Fourier transform of the data, you can reconstruct the image of the head. That's how it's done. I think it's fascinating, and I hope I explain it in a way that people can understand. And the Nobel Prize, right? Pretty cool. Now, just one more image, one more thing to show before I open it up for questions, and that is that there can be artifacts. And again, you have to be careful about, what's your data that you're receiving, and what's the information you're presenting, and how are you displaying it, and how is it being perceived. And in this case, these reconstructions can have artifacts that will, if you don't understand them, can affect the diagnosis. The easiest one to see here is on the right. This is a spine, right? This is somebody's spinal column. This is a section through the body at a particular level. So if the patient was standing up, this would be a horizontal section of the patient. This is the spine, and the patient has a implanted metal screw, a bone screw. And that metal bone screw is creating artifacts in the image. The density is so high that when you do the reconstruction, there are artifacts created from that thing. And if you don't know that that's going to happen, now this is obvious, but what's not obvious is the middle image here, right? What's this big dark thing right here? This happens to be an ultrasound image, and this dark thing is the shadow from that white thing. So there's the ultrasound energy traveling through the image, and it's hitting this. This is reflecting the energy back, and the system is detecting that, but the system isn't seeing any energy reflecting from back here. Well, that's because it's being shadowed by that object. And so again, if you didn't know that, you'd say, well, there's an anatomical problem there. No, it's just a shadow from that there. So you have to understand what your source is. You have to understand what your detector is, and you have to understand, how your detector is being fooled, by what's going on from the physics. So with that, I am going to say thank you. If there's any questions, please ask any questions, and then I'm happy to answer them.
Yeah, thank you very much, Jeff. This was very informative. Really loved the talk. I really appreciate you taking the time out of your busy schedule. So we have quite a few questions here, and I'm going to hand it off to Brian, who's going to be moderating the Q&A session. And again, for anybody who's listening to this and has questions, you can type in the questions in the chat window, and we'll hopefully be able to get to it. Brian, take it.
Hey, thanks, Tim. Yeah, thanks again, Jeff. Great presentation, as Asim mentioned. I just want to say thanks for not bringing up convolution.
I
may
didn't
have triggered
very
some
advanced from
people.
equation either. So there you go. I stay away from equations completely.
It was very good. Yeah, so just get into some of the questions. So what do you think the best modality is for breast biopsy procedures?
Wow, breast biopsy. So breast biopsy is a therapeutic thing, and it's not really imaging. They do imaging while they do biopsies sometimes. So I'm not sure if you're talking about for detecting something in the breast, because the biopsy is the physical act of removing a portion of the breast. So I'm going to answer this two different ways, just to see if it helps. If you're doing a biopsy with a biopsy needle, and you're guiding that needle to the site where you want to take the biopsy, ultrasound scanning and imaging is fantastic. Really good at that. And people that do it with ultrasound guidance really know what they're doing, and it's great. For really small lesions that are hard to get to, you could do interventional MRI, where you have a patient in an MRI system, what they call open MRI. And you can actually place markers using an MRI system, and then you can use the marker to get the biopsy later in the procedure. So I hope that answered that question. I'm not sure if it did or not.
Okay, thank you. I didn't see any follow-up. So going on to the next question, are you able to describe what image fusion is and how it's being used in medical imaging today? Also,
did you say image fusion?
Yeah, image fusion. And have there been cases where image fusion has occurred with more than two modalities?
So I am not familiar if there's been more than two modalities. Image fusion, just obviously the combination of multiple modalities. I can tell you that, again, I know more about ultrasound than I do about MRI or any of these other techniques. I can tell you that in ultrasound, it's phenomenal what they're doing, because what they're doing is they're combining the direct image, that you have. Let's say you have a 20, let's say you have a 5 megahertz transducer, and you do a scan of an object, of a person. There are harmonics of that transducer, unless one of them is 10 megahertz. So you can take a 5 megahertz transducer, and you can also simultaneously get the 10 megahertz information, and you can put those two pieces of information together and create phenomenal. And I've seen them. These are actually being used right now in devices that are in the market used today. And this has only been around in the last 10 years or so that they've been able to do this. So they're clearly the fusing, if you will, or the adding of multiple information is phenomenal. I'm not an expert in that, so I don't know anything about what they're doing in CT or MR or the other ones. But I can tell you in ultrasound, it is opening up a whole new world of diagnosis.
Oh, excellent. The next question, so it was stated that the MRI needs to have a stroke to generate the vibration. Now, is this a physical vibration in the tissue or a vibration of the magnetic field?
I'm not clear of the question. I might have misspoke or been misunderstood. When I was talking about vibration, I was talking about ultrasound imaging. I don't remember talking about vibration in MRI. Oh, I see what you're talking about. No, yeah, nuclear magnetic resonance imaging. I am not an expert in MRI, but what I can tell you is, what I do know is when you apply the electric field, you will align the cellular structure, like the water. You will align the water molecules in the cells, and then when you release the magnetic field, those molecules will relax back to their original position, and when they relax back, they emit a radio signal, and that radio signal is used to create the image. The radio signals are collected, and then they are processed to create the image. So that's what I was trying to say. I hope I did it justice.
Okay, good. Now, does the next question, so does the Nyquist frequency impact the resolution of the imaging technology in terms of resolving detail?
Oh, wow, that's a great one. I mean, the Nyquist criteria states that you can't safely or you can't reliably sense anything less than half your Nyquist sampling rate. There's all kinds of tricks that are played with zero padding and stuff to deal with that. But obviously, the Nyquist criteria defines right what the limit of resolution is going to be, for your sample. I don't know of any way that people, and I wouldn't put it past us. I mean, I really wouldn't put it past us to be able to break the Nyquist criteria. But I don't know of anybody doing it. So if somebody knows more about that, I would want to know. So send me an email, let me know. But no, I don't know of any way of doing
that. Okay, it sounds cool. The next question is related to the future of medical imaging technology and where it's trending. So is it trending more simplified and accessible imaging systems, such as like ultrasound, or is it trending more complex, such as MRI or fluoroscopy?
Yeah, I'll tell you what, it is doing both. I would agree that it's doing both. Let's talk about, again, I'm sorry I always do this first, but I'm an ultrasound guy. Let's talk about ultrasound. They are creating now ultrasound systems that you can run off of an iPhone. So you have an iPhone, you can go to a trip somewhere, and you can use your iPhone with the transducer, and you can do an ultrasound image. Truly astounding. The technology is phenomenal. Densely packed electronics, the power consumption, power control. I mean, it's just really astounding. I'm not sure that's simpler, right? The questioner used the word simple. I'm not sure that's simpler. It's smaller, more compact, and more accessible. But it certainly isn't simple to do it. And then on the other end of the spectrum, yeah, the systems are just getting. I mean, the magnetic, like MRI, I think 10 Tesla. I mean, I haven't searched lately, but I've been, I'm aware of a 10 Tesla system. Yeah, it's getting crazy. I don't want to speak to the value of technology and whether it's worth it or not, but it's going both directions.
Yeah, the 10 Tesla system, I think I've seen images of that. That's just a monster system. And I think they've got a system up in Minnesota, University of Minnesota. But getting to the next question. What do you think the best imaging modality is for viewing or measuring actual blood flow?
Oh, ultrasound! Come on, you guys are giving me softballs there. Again, I'm going to be honest. I am biased. I am an ultrasound guy. So yeah, I mean, Doppler flow is phenomenal. You can Doppler flow of vessels. I know there are people that are doing research on vascular flow into viscera. Using boluses of microbubbles, and they're looking at ultrasound imaging where they take a bolus and they image it as it goes through. So they might use a different imaging modality, but they're using ultrasound and combined. So yeah, it's phenomenal. And again, it might just be because that's what I know, and I'm not familiar with how the other modalities would image blood flow.
The next question is, do you think that ground penetrating radars may have a future in medical imaging by filling the technology or medical gaps and all the other techniques that you discussed today?
The quick answer is yes. The more specific answer would be advances in modalities. Going back to my electromagnetic spectrum and the fact that we are imaging across the entire spectrum. If it's possible to do, we're going to image with it, right? You know what I'm saying? We're going to use it to image. Things that are learned in a different field, and I would say, in ground imaging radar, or any of these techniques that are used outside the medical field, will easily cross into, and medical technology can cross out of, into the other arenas. So I think, yeah, there's a lot of cross fertilization. of the technologies. And my recollection is most imaging technologies came from other sources, like X-rays. Imaging came after X-rays were already used to image other things. Ultrasound came about as a result of radar radar imaging from the war. I mean, it's just fascinating how all this stuff happens.
Yeah, and then now we got computer vision, and that's the next gen interesting stuff. So I think the final question is that, can you make some comment comparing the conventional PZT based ultrasound imaging and newer MEMS based ultrasound imaging and its future?
Well, I'm not even familiar with what you just said. What did you say? Normans?
MEMS is the
micro machining.
Yeah, microelectric.
I got you. Yeah, I'm sorry. Yeah, MEMS. Okay. I don't know enough about the MEMS and what's going on in MEMS to really be able to answer that well for you. But what I can say is that the MEMS stuff tends to be very high densely packed, very small arrays that I've seen so far, right? And I think they're going to have great applications in very small areas. I mean, that's not the way to phrase it. Niche. They're going to have niche applications. For example, intraocular pressure measurement using MEMS ultrasound technology is something that I've seen and heard about. And it's interesting, and I think it has potential. So I think it's fascinating. It is an area that's being researched right now, but I am not an expert in that area.
Okay. Well, if anybody doesn't have any further questions, that was the last question. We'll just maybe give 5 seconds to see if anybody has any further questions. All right, 5 seconds are up. All right, Jeff, I really appreciate you taking the time today and giving us a great introduction on medical imaging. And everyone for joining, we appreciate it, and I hope that you were able to get a lot out of the discussion.
I appreciate the opportunity, and thank you very much.
Well, thank you, Jeff.